You can see my slides, right? Okay. I guess you can see. Okay, so to start with, so as if you don't know me, I'm okay, one second. Yes. So I am Sauravi. I'm an PMRF fellow from Indian Institute of Science, and currently I'm doing PhD in soft condensed matter. So this course is on electromagnetic theory. So in the last class, what we had discussed was basics about vector algebra, where we spoke about gradient divergence and curl, and then we started with electrostatics and the basics of how we can define electric field and stuff like that. So what I'll do today will be again a continuation of the last class. So this should be week 2. Okay, so it's a continuation of the last class. And to start with, we'll again here we'll discuss some of the basic concepts, some theory, and then we will try to solve some questions. And if you have some doubts, we'll try to clear them. So we had discussed in the last class that there is this vector differential operator, the del operator, and this is how it looks. Okay. And then depending on what you are operating on, so whether that's a scalar field or a vector field, you can define different kind of operations. Okay. So if you have a scalar field, suppose phi, which is a function of position, so it's function of x, y, and z, suppose, and now it's differentiable scalar quantity. So what you can define is you can define the gradient of phi. Okay, and this is how it looks. So this is a vector. The gradient of phi would be a vector. And what is the direction of the vector telling you? It's telling you the direction of maximum change. So in the last class, there was this question that what is the physical significance of gradient divergence and curl? So the physical significance of gradient of some scalar quantity is that it tells you the direction, it tells you the change in the, so the maximum change and the direction of maximum change. Okay. And then if you take the component of grad phi along some particular unit vector, then you would get the directional derivative of phi in that direction. So that is the rate of change of phi in that direction. Okay. So that is the significance of gradient. And then when you come to divergence, you would see that divergence actually tells you, as the name suggests, it tells you how the field lines diverge from a point. So if you have some vector field, how does the field diverge from a given point? That quantity is like it's quantified in terms of the divergence. Okay. And then curl tells you if there is a rotation of this field involved in the point that you are considering. Okay. So at some particular point, if there is a tendency of rotation about that point of the field. So that is given by the curl of your vector field. Okay, and this is how these are defined. And these are some of the formulas which are very useful in solving and deriving all the things that we'll be doing in the coming future. Okay, so now suppose if you are given this scalar quantity phi, okay, and you want to find grad of phi at a particular point. Okay, so all of you know have understood about gradient and how to find grad of phi, right? So can you tell me the answer for this question? I'll give you some time. Just try to solve it and tell me what's how the answer would be. Any question regarding gradient divergence or curl and anything you can ask me. You guys are trying, right? Any issue or you're just trying? If you are stuck somewhere, just let me know. So this is how the function looks, right? The operator. Should I share the solution? Okay, guys, you're following, right? Because I'm not getting any response. I'm kind of confused. Okay, anyways, I'll share the solution. So this is how it is, right? So you operate this is your operator, the del operator, and you operate it on phi, and this is what you get, right? And then if you put the values of the point like x, y, and z, then you would get a vector. So this is your grad phi, and it has a direction. It tells you the direction of maximum change of this quantity phi. Okay. Now, this thing would give you a better idea about what grad phi is, right? So the question says that we need to show that grad phi is a vector perpendicular to the surface phi equal to constant, where where c is some constant. Okay. So that means, suppose this is one surface where your phi is equal to C1. Then there's another surface where phi is equal to C2. So for all of this surface, what grad phi would be? So grad phi would be perpendicular to the surface of constant phi. Okay. So how do you prove it? Is that you take some position vector r, okay, at like some position vector given as xi cap plus yj cap plus zk cap, okay, and then about that point, if you want to take a dr element, how will that look like? This would look like dx I cap plus dyj cap plus dz k cap, right? And that lies in the tangent plane to the surface P. Okay, so P is some point on this surface, phi equal to constant, and then you take this element dr, okay, which lies in the tangent plane. Now, what you do is you know that d phi should be equal to 0. Why? Because phi is constant, right? So d phi is equal to 0. That means del phi del x dx plus del phi del y dy plus del phi del z dz equal to 0. So this can again be written as this dot product, right? And this dot product is actually equal to delta phi dot dr. Now, delta phi dot dr is equal to 0. Dr individually is not equal to 0. Delta phi is not equal to 0. But the dot product is 0. That means the angle between them is 90 degrees. So this tells you that the gradient of some scalar quantity is perpendicular to the surface of constant of a surface which corresponds to some constant value of that scalar, right? So this is another significance. Like if you want to visualize what grad phi is, this gives you a visualization. Okay. And now if you are suppose asked to find a unit normal to some surface, so this is some given surface, you want to find the unit normal to the surface at some point. So what do is you find grad of phi, okay, that gives you the vector which is perpendicular to this surface. And because you know the point, you can put the values of x, y, and z. And obviously, again, if you have to find unit vector, you divide by the magnitude. So this is what you do. And this is in a way giving you the unit normal to the surface. Why this kind of questions are important is because this tells you how to use these tools, right? These operators. So in the coming course and also in other courses, whenever you are supposed to use the gradient, the divergence, and the curl, you would this exercise would tell you how to use this operators. Okay. So now, if you have to consider now the divergence, this question gives you a physical significance of what divergence is. Okay. So this tells you that suppose if you have some fluid, okay, and it's flowing in this direction. So V is the direction of your velocity in some fluid, okay, of some fluid. And then what you know that V is function of X, Y, and Z. Okay. So now when V is directed in this direction, so if you consider some volume element inside this container, or suppose this is a pipe and you take a volume element inside that, so you know that in this plane there would be some velocity, okay, and in this plane there'll be a different velocity, right? It would change as a function of X, Y, and Z as you were changing, because V is a function of X, Y, and Z. So if you take that into consideration, so just following up with the figure, you consider that the x component of velocity at P, some point at the center of this volume element, is V1, okay? Then what would be the component of velocity, like x component of velocity at this space? It would be V1 minus half of del V1 del x into delta x, right? So that gives you so you are considering the change of V along x in this direction, right? And then what would be the component at this space? It would be V1 plus this quantity, right? So now if you want to find the volume of fluid crossing this so volume of fluid crossing this plane, okay? So AF, okay, E and D. So something which crosses this plane. What you have to do is you have to multiply by dy and like delta y and delta z. Similarly, here again, you are multiplying it by delta y and delta z. So the difference between these two would give you the loss of volume per unit time in x direction. Similarly, you can find the thing in the y direction and in the z direction. So now if you consider the total loss of volume, what are you getting? You are getting del V1 del x plus del V2 del y plus del V3 del z. And that is nothing but the divergence of V. So this tells you that divergence of V is actually something which tells you about what is so it gives you an idea about the flow of or whether there is some loss of, here in this case it's fluid. So loss of fluid somewhere while it's traversing some volume, right? So now if there is no destruction or creation of fluid, and if it is conserved, in that case it would be solenoidal. And what we mean by solenoidal is that, yes, any question? Right. So in that case, divergence of V would be 0. So you would later see that divergence of electric field would also have some physical significance in terms of the charge density. Okay, that would come up in the coming slides. So this is a physical significance of divergence. Okay. So now suppose this is your sum vector which is given, and you want to find, this is a question, just a question to get used to this vector operators. So this is your given vector and you know that it's solenoidal. What do you mean by that? Is divergence of V is equal to 0. And then you have to find A. So what do you do is you consider divergence of V to be 0, right? And from there, what you get is the value of A. So that means whenever you have to specify or characterize some vector field, you need two things, minimum two things. One is the divergence of the field and another is the curl of the field. While in case of a scalar field, if you know the gradient, it's enough to describe the scalar field. Okay. Now what is curl is, again, see, if you plot the rotational flow of water as vectors and measure it, so then that gives you curl. So curl is a measure of how much a vector field circulates or rotates about a given point. Okay. And this is the convention. So if the flow is counterclockwise, it's considered to be positive and clockwise is negative. Okay. So again, this curl of any vector being 0 also has a physical significance, right? So when curl of some quantity, some vector v is 0, it is called irrotational vector. Okay. And hi guys, any question? Lahari, any question? If you don't have any question, can you please unmute yourself, mute yourself and your video? And if you have a question, please ask. Okay. So we would see that even from the knowledge of curl of electric field, suppose if you have an idea about what is the curl of electric field, that would also give you a physical significance of conservative fields, which we would gradually come to. Okay. So any vector quantity can be described in terms of its divergence and curl. So like here, you have this vector field. Okay. And here it's said that you have to find the constants A, B, and C so that this vector field is irrotational. So it's a similar kind of question. So what you do is you find the curl of this vector, okay? And then you equate each of these components to 0 because it's said to be rotational, and that gives you the value of A, B, and C, right? And now if you know that, you know the curl at different points in space. So this point, this part is very important because this will lead you to the concept of potential. Okay. So it's said that now you know that this vector is irrotational, so that this vector can be expressed as a gradient of a scalar function. Okay. So we assume that this vector can be considered as gradient of some scalar function phi. Okay. And this is how it's written, right? Okay. So you know this is how gradient is defined. Okay. So now if you compare this components with this component that you have just defined, this is what you get. So del phi del x is equal to x plus 2y plus 4z. Again, del phi del y, that is the jth component, is given as 2x minus 3y plus z minus z. And this is the kth component, right? So now you have 3 equations and 3 unknowns. So what you can do is here you can integrate one partially with respect to x, and this is something that you get, right? And this is some constant which you can consider to be function of y and z, right? Similarly, if from 2 and 3 you get some phi as something plus a function of x and z, again something as and function of x and y, right? So now if you compare this 3, 4, 5, and 6, what do you get? You get that you can consider f of yz as this gxz, like function of x, and so you can take up the functions of x and z, and that can be your g. Again, you can choose the functions of x and y, and that can be your h, right? And then if you arrange and take all the terms together, this is something that you get, right? So this is your phi. So what you note here is that now, if this is your phi, so what did you get? For your vector field, which was irrotational, you got some phi, some scalar, the gradient of which is equal to this vector, right? So that means V, which is whenever a vector can be expressed by a gradient of some scalar quantity, it's called a conservative vector field, okay? And this phi is called the scalar potential. Similarly, you would see later that in case of electrostatics, where the curl of E is 0, you can consider the electric field as a gradient of some scalar potential V. So where V is your electric potential, okay? So this gives you this concept, this mathematical concept leads you to the concept of potential, okay? Right. So clear till here, right? To everyone? Anybody has any question regarding gradient divergence and curl? Okay, so if not, then let's move forward to Gauss's law. So now what we will be talking about is, so we already know the basic formula, that is the Coulomb's law, and how we can find the field for some distribution or some point charge or some discrete charge distribution or continuous charge distribution. We know the basic Coulomb law. But now what we will see is that there is this Gauss's law, which in a way doesn't give us anything new, but this gives us a very strong tool to calculate fields in cases where we have some symmetry. So we can make use of the symmetry to find fields very easily. Okay. So what this tells us is that now you know that this is the field for some point charge q, right, at a distance r. And if you draw the field lines, this is something it would look like for a positive charge. And so if this in a way tells you how the magnitude of your electric field or how the strength of your electric field is decreasing as a function of distance, right? While here, what it is just telling you is it's telling you some field lines. So you just looking at it, how do you tell that your electric field intensity is gradually decreasing? So there, what you say is, you say that here the density of field lines are much more, while here the density of field lines are less. So in a way, this density of field lines, or how many field lines cross per unit area, can tell you about what is the flux of electric field through some particular surface. And that is actually a measure of the field intensity at that place. Okay. So suppose if you have some area, some area vector, okay, so this is your area vector dA, some surface, and there are field lines crossing that surface. So you define the flux of E through the surface as E dot dA. Okay, so it's a surface integral. Okay, so this is called the flux. Now, what this tells you is, as you can see, so flux is dependent on the electric field intensity, right? Now, the Gauss's law links this to the amount of charge that is present inside a volume. So what this tells us is that now if you have some flux and there's some flux through some closed surface, it's a measure of the total charge that is inside. And that is what the Gauss's law tells you. Okay. So suppose if you have some charge Q outside, what would happen? The flux line, the field lines would cross the volume. So it would go past this surface, right? And then it would come out of the surface. So the net flux here turns out to be 0. But when you have some charge inside, what would happen is you would have a net flux that would be crossing the surface. So in a way, all charges that are inside some volume would affect the flux that crosses the surface enclosing it. Okay. So in the case of a point charge Q at the origin, the flux of E through a sphere of radius r surrounding the point charge would be given as something like this, right? So you consider a sphere and you take some volume element of the sphere, okay? And this is sorry, not volume. You take a surface element, okay? So dA can be written as r square sine theta d phi, where r is your radius, okay? And then this is your field value that you already know, right? And if you do E dot dA over this surface, what will you, over the entire surface enclosing the volume, so over the entire sphere here, what will you get? You would get Q by epsilon naught. So you can see that flux is related to the charge that is inside, right? So this is what is the main concept. And now if you have a number of charges and if you have some distribution, it would follow the principle of superposition. So what you get then is the total enclosed charge. Okay. So closed integral of electric field over some surface is given as Q enclosed by epsilon naught. So this is your Gauss's law. And we would see how this is useful. So now what you can do is you can change it to a differential form using the divergence theorem. So divergence theorem links the surface integral with the divergence, right? With the volume integral of divergence. So if you do that, what you can now write is you can change the surface integral in terms of the volume integral, okay? And then you know that if there's some charge density, volume charge density rho, your total Q enclosed would be rho d tau, where d tau is your volume element, right? Over that volume. So now this same thing, this integral form turns out to be this in the differential form, right? And from there, you get an expression which links the divergence of electric field to the volume charge density in that volume. Okay. So this is the Gauss's law in the differential form. Now, suppose this is a question which makes use of this theorem or this law. So here we know that suppose the electric field in some region is found to be E equal to k r cube r cap. Okay, it's in the spherical coordinates where k is some constant. Now you have to find the charge density rho. So how do you do that? Can you tell me what the expression for the charge density will be and which formula to use? Anybody?
Operate in one direction. So they are saying they have rectified this and how they can solve, how they can do this, no Stokes law.
Anybody? So whoever unmuted, do you have anything to say?
Ma'am, epsilon E is equal to D, correct?
Epsilon E?
Epsilon E is equal to D, flux density. D is equal to epsilon E.
Yes, right. That's fine. So I haven't
charge
gone
density means here
So
the del dot E is equal to rho by
right.
epsilon.
So what is charge density? Charge density is the amount of charge per unit. Like if you talk about volume charge density, like here we are talking about volume element and volume charge density. So volume charge density is charge per unit volume, right? And that is given as
Yes.
rho here. Okay. If you have some surface distribution, like some surface charge, so there the total Q would be given as sigma into dA or ds, where ds is your surface element and sigma is your surface charge density, right?
Yes, ma'am.
Right. What you are talking about, D equal to epsilon E, comes later. I'll come to that. That is electric field displacement. That will come later. There, that is linked with the free charge that is present in your system. So I'll gradually come to that. But the question here is asking is that you know the electric field, okay? But you want to find the charge density rho. So you have to use this formula, right? So
yes, ma'am. Del
yes,
dot E epsilon naught is equal to rho.
right. So can you try to solve the divergence of electric field? This is your electric field that is given. So what would be the divergence? So it's in spherical coordinates. So you have to use the expression of divergence in the spherical coordinate.
Sorry. 3K. Maybe.
So it's
D by D or
3K R square.
3K R square.
Okay, okay. So this is what you did, right? I can hear my voice. Some kind of feedback. Okay, okay. What's Anyway, so this is what you did, right? So this is your expression of spherical coordinates, like divergence in spherical coordinates. Can you guys just unmute it? Like mute once. I can hear my own voice. Okay. I can still hear it. Okay, fine. Anyways. So now what you can do is you find the divergence of E, you multiply by epsilon naught, and this gives you rho as a function of R. That is your radial quantity, right? Clear? And now that you know rho, how to find the total charge? And as the question suggests, there are two different ways. Any idea, guys? Okay, one thing. You said 3K R square, right? So what you guys were doing was just del R. But see, it's not similar to just del X, del Y, and del Z. The thing that you do for rectangular coordinates. Okay. You have to. So you remember how we move from rectangular coordinate system to curvilinear coordinate system, right? And there you had the scale factors. Okay. What's happening? Second. My audio is not clear, right? Can you guys hear me properly?
No, it's still echoing.
I can hear my own voice. I don't know why.
Jenkins, Suji, can you please mute yourself? It will be solved. Thank you.
Yeah, thank you. Can you guys hear me now?
Yes, it's better.
Right. Okay. So one second. So what I was telling is that, see, when you were doing what somebody answered it as 3K R square, right? But it's not just del R, del phi, and del theta when you go to spherical coordinates. You have to consider the conversion from rectangular to spherical, where you have to go through the entire process of including the scale factors, right? So if you remember, we shared or we discussed about the gradient divergence and curl expressions in different curvilinear coordinate systems. So you have to use those expressions for corresponding to the spherical coordinates. So in spherical coordinates, this is how the R or the del R term looks like. It's 1 by R square del R of R square into ER. Okay. So if you do that, Here it has no dependence on theta and phi, so we are not considering those terms. So if you do that, this is your, so your divergence of E comes out to be this, right? And then you multiply by epsilon naught. So this is your rho. So now that you know the charge density, what are the two ways of finding the total charge? Any idea?
Multiplying it by the area we have considered.
Volume, right? This is volume charge
unit.
density.
Yeah.
Yes. So one way would be to use this expression and doing a volume integral. So this is what you are talking about, right? And what would be the other way? There's another way of doing it. See, there you know the electric field, right? So what does the Gauss's law tell you? The Gauss's law in the integral form has a relation between electric field and the charge enclosed, right?
It's d dot ds.
E dot. So
E
here
e-
we
yeah.
right. We have not gone to the description of electric field, like the electric field displacement yet, right? Here we are just talking about the total electric field. So what we use is, so there are two ways. One is obviously rho d tau. This is something that you just said. But there's another way which directly uses the Gauss's law. So you know the electric field. What you do is a surface integral, okay, over the surface of your sphere, and then you multiply by epsilon naught. That also gives you the total enclosed charge. And as you can see, both of them are same, right? So if you know the electric field, you can directly go to the total charge that is enclosed. You don't need to find the charge density each time. But obviously, you can find the charge density and do a volume integral as well. Okay. So now, this is another question. Here, I guess we have, this is a very common type of question, and we have seen these questions. Many of you might have seen these questions. So what it says is that you have this charge at one corner of this cube. Okay. So what is the flux of electric field that passes through this shaded side? So can you tell me how to proceed with this question? It makes use of the Gauss's law.
Epsilon naught.
Yeah.
Not Q by epsilon naught.
Q by, what is the factor you just said? I lost you.
The flux will be Q by 6 epsilon naught.
Why do you say 6?
Because it's from one side, right? Like one side is actually shaded. So
Yes, one side is shaded, but what does Gauss's law tell you? Gauss's law tells you that, see, if in order to use Gauss's law, you have to have a volume that encloses the entire charge. The charge is sitting at one corner here, right? So it's not enclosed. It's exposed on the surface, right? It's at the corner. So in order to make use of Gauss's law, you have to have a volume which encloses this charge. So if your charge was somewhere here inside this cube, it would be correct, right? You have 6 surfaces, so you give it as Q by 6 epsilon naught. But now your charge is at one corner of your cube. So it's not enclosed. So if you do a surface integral, there'd be a point where it would be undefined, right? Because your Q is sitting at this point. Any idea how to tackle this issue? Okay, so what you can do, you can have more such cubes, right? So as to cover the entire charge, like enclose the entire charge, something like this. If you have 8 such pieces, possible, right? So if you do that, then what happens is, now how many such surfaces do you have? 1, 2, 3, 4, and then there are 6 such surfaces, right? So total it would be 24 such squares. So the total flux would be obviously E dot ds, but then the flux through only this part of the surface would be 1 by 24th of this. So that would be Q by 24 epsilon naught. Is this clear to everyone? Okay, so I guess it's clear. Okay, now this is another question. Here you have a long cylinder which carries some charge density that is proportional to the distance from the axis. So the charge density rho is equal to k is some constant into s, where s is your radial coordinate here. Okay, so in the cylindrical coordinate system, it's given as s in this question. So now you want to find the electric field which is inside this cylinder, right? So what the picture has considered is, they have considered some some volume element, some volume inside the cylinder, and then in order to use your Gauss's law, what do you have to do? If this is your surface, okay, and you want to find your field at a distance s from your axis, you have to consider the total charge that is enclosed by this volume, right? And then what is your surface element that you are considering, and you have to do a surface integral, right? So can you tell me how to proceed? Like, how exactly should we proceed with this question? So if you consider E dot ds, what would be your ds here? Or what would be your, like, what would be the surface over which you want to find your electric field integral? So from symmetry arguments, you can see, right? So you have some charge inside this volume, right? And it has a symmetry over this axis. So that means there would be field lines in this direction, emanating from like this, and then there'll be field lines in this direction, right? So it would all start from the axis and gradually move in the radial direction, right? So that means when you do E dot ds, so you have to consider the surface like this curvilinear surface, right? So that your area, like the area normal, makes an angle of 0 degree with your electric field. If it's perpendicular, that's like E dot ds, that term would go to 0, right? Your electric field is directed in this direction. So only this surface, the curved surface of your cylinder, would actually contribute to your electric field, right? So what I mean is that, so this is your cylinder that you have considered. Okay, this is a Gaussian cylinder of some length L, and S is your radius. So now Q enclosed would be rho d tau. This is your volume element for cylindrical coordinates. Okay, and if you put that, this is the expression you get for the charge that is enclosed within this small Gaussian cylinder, right? And then here, what you do is, that electric field is pointing radially outward. So the curved surface would contribute to your integral. Okay. So what you do is you take the electric field because it's independent of dA. And what is your curved surface area? That is given as 2 pi s into L, right? That is your this surface area, 2 pi s into L. Okay. And then if you equate both of them, you get the electric field value. And as you can see, it has a radial component. Is this clear? Clear to everyone?
Yes, yes.
Right. And now, so using the similar concept, so all this Gauss's law applications would be based on the same concept, that whenever you have to find the electric field in some region, you have to consider what is the charge enclosed in this region, okay? And then you have to consider what is the surface element that contributes to your integral, and then equate the two, right? So this is a hollow spherical shell, and this is the charge density. It goes as k by r square. And then now you have to find the electric field in 3 regions, right? R less than A, R which ranges from A to B, and R greater than B, right? And then you have to plot how the electric field magnitude looks like as a function of R. So what is straightforward from Gauss's law is what is the field that is inside. So for 1, what would be the field for R less than A? Any idea, guys? So you have charge, volume charge density, which is distributed over this annular region, right? Over this shell. Yes, it should be 0, right? Why? Because there is no charge enclosed anywhere for R less than A. Okay. So for 1, it should be 0. Now, what would happen for 2 is you have to now consider a sphere of some radius r which comes between A to B. And then you have to consider what is the charge that is enclosed within that sphere, right? So it's something like this. So what you do is you consider a sphere of some radius r, where r ranges between A to B, somewhere in the middle of this space, okay? So what would be the area element? So it would obviously, it would be 4 pi r square, that is the surface area of your sphere, okay? And what is the Q enclosed? So this is your area, like volume element, and then you do an integration over r theta and phi, okay? And then the integration would be from A to r, right? The integration over r, over the radial quantity, should be from A to r, the radius that you have chosen, okay? And if you do that, this is what you get, right? And then for the third case, when r is greater than b, what would change? Everything would be same now, right? Everything is similar to this space. But now here, when you are integrating, you have to integrate from A to B, right? Because you are in that case, you are considering a sphere of some radius greater than B, okay? But then the charge is distributed only from A to B. So when you integrate, your integration in that case should range from A to B. And if you do that, you would get something like this, right? So again, here what you see is you have this 1 by r squared dependence that's coming in. All of these are constants. So you have 1 by r squared dependence, right? So if you plot it, it would look something like this, right? Clear? Okay. So now we would come to curl of E, and we would see how curl of E is useful in defining the concept of potential. So as I said, that this is the expression for field due to a point charge, okay? And then what we can do is, now you know this is your electric field. What you do is you consider some region, some line integral from some point A to point B. Okay, suppose this is your some point A, some point B. You have a line. you want to do a line integral of this electric field over that line. Okay. So this is your in spherical coordinate. This is your how the line element looks like. Okay. So you have to do E dot dl, and this is how it looks like. And then you integrate from A to B. So if you do that, you get something like this. So now if you have a closed surface, okay, so you start from A and you come back to A, right? If it is a closed integral, what would happen? RA would be equal to RB because A is equal to B. And then E dot dl turns out to be 0. So the closed integral of E dot dl comes out to be 0. Here we make use of this theorem. So just like the divergence theorem, which relates the surface integral with the divergence of a vector quantity, here what we do is we relate the curl of a vector quantity, the surface integral of curl of a vector quantity with the line integral, right? So now we know that E dot dl is equal to 0. So if you compare with this, this means that curl of E or the surface integral of curl of E should also be equal to 0, right? If you use the Stokes theorem, use it here. This is what you get. And now that you know that we had just solved a numerical which says that whenever the vector, the curl of a vector is 0, you can express the vector in terms of a gradient of some scalar quantity, right? And this is what is again done here. So this tells you that now you can express E as gradient of some scalar quantity V, and this is your electric potential. So electric potential is a scalar quantity. Minus sign is a convention. Okay. So this is how you come to the concept of electric potential. Okay. And one can use this concept to relate potential with the charge density. So this is something we just saw, right, from the Gauss's law. Divergence of E is equal to rho by epsilon naught. And now we know that in case of electrostatics, your curl of E is equal to 0. Okay. So if you now use both of them and if you use this identity, what do you get? You know that you can write E as minus grad phi or grad V, right? So if you put that here, you get del square V is equal to minus rho by epsilon naught. So this in a way relates your potential directly with your charge density, right? And now if there's no charge in some volume, that is you have some volume with no free charge or no charge density, what happens? Your rho is 0, right? And then what you get is Laplace equation. So divergence like del square V is equal to 0. Now it's important to remember, and I think this type of questions might come in your assignments as well, that any solution to this Laplace equation are called harmonic functions. So whenever your potential or some scalar quantity, if it satisfies this equation, these are called harmonic functions. So just to recall, when curl of a quantity, some vector quantity is 0, it's irrotational. When divergence of some vector quantity is 0, it's solenoidal. Okay. When some scalar quantity satisfies the Laplace equation, it's called harmonic functions. Okay. And this in a way relates all the formulas that we have been deriving and discussing till now. So it relates how we can go from potential to charge density to electric field and vice versa. So try to understand and remember these relations. Okay. So now many of you have been talking about D many a times today. So what is D? What is this D? So this D is the electric displacement. So initially till now, we have been talking about electric field and we have been talking about the charge density or the volume charge density rho. Now, this charge density can arise due to two main things, right? One can be bound charge, another can be free charge. Free charge means the charge that is like, suppose if you have some charge density, you have applied some, so you have some discrete charge distribution, or when you say that you have a line charge density of lambda. So all of this, whatever you are providing or whatever is accessible to you, this information of explicitly providing the charge to somebody, so that is a free charge. While the presence of electric field or presence of charge nearby can induce a polarization in your substance. And that can result in some new charges, which are called bound charges. Okay. So in a way, your total charge density rho can have contributions from bound charges and free charges. Okay. And so for now, remember that one can express this bound charge in terms of the polarization. And this is how the relation looks like. Okay, it's given as minus grad of P, divergence of P, where P is your polarization. Okay, so I think in the coming classes, we might have to derive this. Or else if you want to see the derivation, you can look it up in any standard electrodynamics books. So this is how polarization is related to bound charges. But then you have another quantity, which is your free charge, right? So if you now consider, if you take this term here, what you get is divergence of epsilon naught into E plus P, where P is your polarization, is equal to rho F. So rho F now is your free charge density. Okay. So if you take this quantity and term it as some quantity D, so that is your electric displacement. So what you can then get from the Gauss's law is divergence of D is given as rho F, where rho F is your free charge, the charge that you are providing, or basically the information about charges that are explicitly known to us is actually always free charge. Okay. And similarly, you can have an integral form, which is a surface integral of this electric displacement, which is equal to the enclosed charge. Okay. So that denotes the total free charge that is enclosed in the volume. So this is a particularly useful way of expressing Gauss's law because it makes reference only to free charges. Okay. And this is the charge that we control. So if you go back to the same example that we were just discussing, and there we had spoken about the total field, here we would just talk about the electric displacement. So we say that suppose this is your, you have a long straight wire, it's similar to the last example. So you have a long straight wire and it's carrying some uniform line charge lambda, okay? And then it's covered by some insulation, as you can see, of radius A. Now you want to find the electric displacement. Okay, how do you do that? So again, you consider this Gaussian cylinder of length L and radius S, okay? And the surface that is contributing to the integral is the curved surface, and its area is given as 2 pi S into L, okay? So D dot dA, this thing, so that is given as D into 2 pi S L, and that is equal to the total charge that is enclosed in this region, and that is given as lambda, which is your line charge density into the length. So lambda into length, okay? And then if you compare, what do you get? D equal to lambda by 2 pi S cap, right? So if you remember, this is the similar formula that we have seen for a line charge density in the last class, okay? And now that you know D, you can again go back to your total electric field, because considering P is 0, what you do is E equal to D by epsilon naught, and this is how it looks like. So if now your medium is not free space and if it has some permittivity epsilon, then D would be equal to epsilon, the relative permittivity of that medium, into the electric field, right? Is it clear? So here, as you can see, you're considering epsilon naught, you're considering P equal to 0. This is because you're considering the values for S greater than A, that is in the free space. But inside this insulation, you can't do that because there it's a dielectric and it can have some net polarization, which you do not know about, right? So this holds when your P is 0, okay? And you can directly relate, in that case, the electric displacement with the total electric field. So this is how we come to the concept of electric displacement. Okay, so now we would try to do some numericals, basically, which makes use of all that we have been discussing till now. So the electric potential here is given, okay, in free space is given, where the charge density rho is 0, okay. So this is your electric potential, and you know that the charge density rho is 0, okay. And you also know that the x component of electric field, that is Ex, and the potential is 0 at the origin. So given all these conditions, can you find Fx? So can you tell me what are the given conditions or what are the equations that we have to solve? Those equations we would try to find Fx from those equations. So what are the different equations or the relations that we have to make use of, depending on the conditions that are specified in the question? So what is the first condition that you can see from the question? Anyone, anything? So see, your charge density is said to be 0, right? Charge density rho is 0. So now if you go back to your relation that relates potential and charge density, what did you get? We just read about this thing, right? So now your rho is 0. So that in a way tells you that del square V is equal to 0, right? So the first condition that you get from here is del square V is equal to 0. Okay. What is the second condition? The second condition is that the x component of electric field is 0 at origin. So you know how to go from potential to electric field, right? So how is potential and electric field related? Can anyone tell me?
E is equals to minus del V.
Right. So then what you can do is you can find the gradient of potential and then you can equate the x component with Ex, right? And then if you put, because it's at origin, so x and y would be 0 at the origin, and that would give you some equation, right? And that would be 0 because that's the other condition that is given here. And another condition is that v is 0 at the origin. So you can put x and y as 0, and then that value would be corresponding to 0. So now if you look at all those equations and try to solve it, you can solve for this unknown function. So what we just saw is this is your potential, right? So rho is equal to 0. That means del square V is 0. So how do you find del square V? You know the operator, and so it's del square V del x square plus del square V del y square plus del square V del z square, right? So if you do that, that is equal to 0, right? Each of the functions would be equal to 0. So if you do that, this is your first condition that you get, right? And then you know Ex is equal to 0 at origin. So you find E equal to minus grad phi, and this is your expression of Ex. You put x and y to be 0. Okay, that gives you this condition. So f prime of 0 is equal to minus 8. F prime means like derivative with respect to x. Okay, and then you put the potential like this condition, v is 0 at the origin. So if you do that, you find that f of 0 is equal to minus 4, right? So then when you try to solve, so this is your condition, right? This is the condition that you get from here. So that tells you double derivative of f with respect to x is given by this quantity here. So if you integrate once and if you make use of this condition, you get the first constant. And then when you integrate again, you make use of this condition, and that finally gives you the function fx. So, right, whenever you're looking at questions like this, try to jot down what is the given information in the question and then use the relations that are known to you in order to find the unknown. So, in this case, your answer would be this 3x square minus 4e to the power 2x. Okay. Now, this is another question. Here, what we see is the electric potential is given in the spherical coordinates. Okay, this is some electric field potential, and these are constants. Now you want to find the charge density at some distance r equal to r naught. So what is the relation that we have to use? Potential V or phi is given, and you want to find the charge density. So which relation to use? Anyone?
Cylindrical coordinate we can use.
We'll be using spherical, right? Because it's in spherical polar coordinates.
Oh,
But that is
okay.
fine. We would shift to our coordinates according to the question. But what is the relation that we'll use? We know the potential. We want to find the charge density. So what is the relation that relates potential with charge density?
Poisson's equation.
Right. So it's given as del square phi equal to minus rho by
Rho V by
epsilon naught.
epsilon.
Right. So this is your phi, that is your potential. So can you use the del square operator and tell me, and then put r equal to r naught and tell me what's the answer? So here you have to use the del square operator in the spherical polar coordinates. I'll give you some time. Let's try to solve. Should I share the solution, or are you guys trying? So I'm giving you time so that you get used to using this different operators in different coordinate system, because in a way you have to get well versed about how these operators look like in different coordinate systems and when to use which relations. This lies at the heart of solving this kind of questions. So the more you do that, you'll get used to using this. Okay. So if I share the solution, it would be something like this, right? So this is the relation that we have to use. And then we have to use this expression, right? This is your, because it's only a function of r. So we just have to take the terms which has derivatives with respect to r. Okay. And all other terms are 0. So del square phi is given by this. So now if you use this relation, you get something like this, right? This is your expression for del square phi. And now here you put r equal to r naught because you want to find the charge density at a given distance. And if you do that, this is your expression for del square phi. Right? And so then you use this relation to find the surface charge density, volume charge density. Clear, right? Clear to everyone? I'll consider that it's clear. Okay. So now this is another question. And here you are given some vector A, and it said that there's some circle of unit radius in the plane, okay, which is defined by z equal to 1 with the center on the z-axis. So this is some circle, and you want to find the volume of the integral. You want to find this line integral of this vector along the circle, along the circumference of the circle. Okay, so it's a line integral. So can anyone tell me how to do it? See, obviously we can individually do it along dx, dy, dz, and change it to radial component and do everything. But in this kind of question, the first thing that you have to try is you have to see how to simplify the question, okay? And now because you have to find the line integral, there's one theorem that should come to your mind, and that is the Stokes theorem. What does the Stokes theorem do? The Stokes theorem relates line integral, closed line, like line integrals with surface integrals of curl of the vector, right? So that means the first thing that you should try in this kind of questions is to find the curl of this vector, because the curl of the vector, the surface integral of curl of some vector is equal to the line integral, the closed line integral of this vector A over the line that is enclosing the surface, right? So try to find the curl of A. So it's pretty simple. So I won't spend much time here. So if you solve it, you'd see that the curl of A is actually 0, right? So that's why, see, you could have solved this question by changing to radial coordinates, okay, and then taking line integrals and changing all of this in terms of radial or cylindrical coordinate because Z is also involved. So if you can do all that, but that makes it unnecessarily complicated. The first thing you should try with this is to find the curl. Whenever you are asked to solve closed line integrals, try to find the curl. Okay, and if your curl is 0, like in this case, your integral should be 0. So the answer is B. Okay. Now this is another question. It's a different kind of question. Here it said that you have 4 equal charges, okay, of plus q, each kept at different vertices of some square of side r. Okay, so you have a square on all the 4 vertices. You have 4 positive plus q charges. Now a particle of mass m and charge plus q is placed in the plane of the square at a short distance a, much less than r, from the center. Okay, so it's placed at some distance a from the center. Now, if the motion of the particle is confined in the plane, it will undergo small oscillations, and we want to find the angular frequency of the oscillation. So it's something like you have some square, okay, and there are all these q charges at this ends, right? Pardon my bad handwriting here. Okay, so, and now here, if this is your center, slightly above this, you have another charge q, right? You want to say that now what would happen? There are these charges, so there would be forces from all the 4 charges, right? That would act on this, on your field point, on this charge q. And you have to find the expression for what that force. Now, if that force, and this is your distance from the center, this is a, right? This is your distance from the center as given here, a. So now if has a expression of something like k into a, where k is some constant, then it has a expression of similar to some simple harmonic oscillation, right? F equal to kx kind of expression. So there k can be actually written as omega square, where omega is your angular frequency, right? So F equal to omega square a, or F equal to omega square x. So in that case, from that constant or the coefficient that you have in front of a in the expression of force, you can find the angular frequency. So what you have to first do is you have to try to find the expression for force from this 4 points, right? So the solution or the process is very simple. The concept is simple, but here obviously you have to, because this a is small, much smaller than r and all of this, so you have to consider this, and that would involve some kind of approximations that you have to do. Okay, so it's something like this. So what you do is you first consider the first these 2 charges, right? So what happens is, obviously here the x components will cancel out. So you'll have only component along y. Okay. So how do you do that? Is something like this. So this is your distance. You find this is r by 2. This is small a. Okay. And it's just Pythagoras theorem that it's being used. And k is 1 by 4 pi epsilon 0. It's just the constant. Okay. Like here, k is not equal to the spring constant k. It's just a constant for 1 by 4 pi epsilon 0 in this solution. So now E1 equal to E2, and this is your term, and then you take only the cos theta component because you only want to take the component along y, okay? And there you have, here as you can see, you have done some approximation, considering that your A is much smaller than R, okay? If you use that approximation, you can simplify your expression. So this is your expression for E1 and 2 along y direction, right? Similarly, you can find the expression for E3 and 4, like the third and the fourth charge along the y direction. Again, the x components cancel out, right? So if you do that, so this is your expression for electric field components for these 2 charges along y. Now, as you can see from the figure, this is pointed upwards, while the field for this two would be pointed downwards. So the resultant field will be the difference of the two. Okay. And this is your resultant electric field, right? So now if this is your expression for electric field, what is the expression for force? Force is equal to Q into electric field, right? At that point. So this is your final expression for the force. Now, as you can see here, it has an expression which is similar to minus omega square A kind of term, right? Where this term is equal to omega square. So from here, you can find the omega, which gives you the angular frequency. So these are some kinds of questions that are asked in competitive exams like JAM or, NET and things like that. So it's pretty simple concept, but just you have to remember how to use it and how to simplify based on the conditions that are given. Okay. So here the answer would be this. Clear, right? I guess it should be clear. It's very simple concept. Okay. Now, this is also another question. As you can see, the charge per unit length on a circular wire is given. Okay. And it's given as lambda naught cos theta. So it's function of theta. Okay. Where lambda naught is some constant and theta is measured from the positive x-axis. And then it said that you have to find the electric field at the center of the circle. So if you have to go conventionally, what is given to you is, the line charge density over along the circular wire. Okay. And you have to find the electric field at the center. So you know the distance of each. You have to consider the distance of each line element along the wire from the center. Okay. Consider a r d theta kind of small element. Okay. And so you have to go to the radial or radial components because you are talking about a circular wire. So all these things you can do, and then you have to do an integration. Okay, the total integration of each line elements over the wire, and that can give you the total field. But what is interesting is to now look at the options that are given to you. So why I have chosen this question is to also for you to see that at times, considering what are the options and what should be the solution, can solve and can save a lot of time and effort. Okay. So here, as you can see, if you draw the structure and just see what is the information that is provided to you. So this is your circular wire, and this is how the line charge density is changing, right? So if you consider that as a function of theta, which is from the x-axis, okay, so here theta is 90. That means lambda is 0 here. Again, here theta is 90, so lambda is 0. Okay. And then as you go to this side, it's 180. So cos 180 is minus 1, right? So it's minus lambda. So this tells you how it visually tells you how the charge per unit length is changing along the wire. Okay. So now because this is a positive charge density, this is a negative charge density, you know that the field lines should start from here. Okay. It should emanate from this point and it should be directed inwards in this point, right? So this again tells you that, and from the symmetry, we know that so what would happen is, because this is how the charge density is being distributed. So what would happen is the y component won't be there. It would cancel out, right? So what would remain is only the x component. And there we know the direction because we have a positive distribution here and a negative distribution here. So we know that the field lines start from positive. So it diverges from the positive charges and it goes and, it merges or goes towards the negative charges, right? So that gives you an idea about what should be the direction. So now if you look at the options, you see that only the first option matches with your idea of how the field directions should be. So that is already telling you that your answer is A. Okay. Okay. Now this is a very standard question. So this tells you to find the potential inside a uniformly charged solid sphere of radius r and total charge q. Okay. So this is a very standard question, but even then I would discuss that because this this is important to understand how to solve it, and also to remember, like it would be helpful to remember what it is telling us, okay, what the solution is telling us. So what we say is, now we consider, we can always orient our axis such that your field point is along Z, okay, just for simplicity of solving. And we know that this is how we can find the potential. Potential is given as 1 by 4 pi epsilon 0 rho d tau by R, okay. So now for our case, we know what R is, right? It's just the vector subtraction. So you find this component, like this vector magnitude. So that is your R, right? This point. So because you have considered some volume element at this point, which is at a radial distance of R, and these are theta and phi. So this is the volume element of charge that you're considering, and you're considering the field at point P. And then you would integrate over the entire sphere. That's how it's done, right? So now your d tau element is given as R square sine theta d theta d phi dr. This is your volume element for spherical polar coordinates, okay? And you can integrate over the entire phi, okay? Phi, so phi has an integration from 0 to 2 pi, and there is no phi dependence otherwise. So you can take the integration outside, okay? And there is a cos theta term here. So this is the integration that you have to solve. And there you can do the substitution and change it to so there are identities of root over a square minus x square kind of expressions, right? So if you use those identities of integration, what you get is something like this, right? So now if you put that here, what you see here is important, okay? So here, this is the expression for your potential, right? Now, you know this is your rho. Rho is charge per unit volume, right? So Q by the total volume. And then if you put the expression, this is the final expression of V in terms of total charge Q, the radius R, and the distance of your point P. So now what happens when Z is 0, right? So when you are at the center of this solid sphere, you see that you get V as 3Q by 8 pi epsilon naught R, right? That is your value of potential for a solid sphere of total charge Q at the center of that sphere. Now, what happens when Z is equal to R? That is when you are on the surface of the of this solid sphere. So there, this term goes away, like it becomes 1. It doesn't go away, it becomes 1. So what happens is, then you get the potential as Q by 4 pi epsilon naught R, right? So all over the surface, it's a constant potential surface, which is given as Q by 4 pi epsilon naught capital R. That is your radius of your solid sphere. And then anywhere beyond that, what will happen? There, you can't use this relation. It's important to remember that whatever you have done here was to find the potential inside a uniformly charged solid sphere. So this holds for all the points inside the sphere and on the surface. But when you go outside the sphere, you have to again go back to the concept of the total charge enclosed within the volume. You have to use Gauss's law, and there we know what the potential would be, right? So it should be Q by 4 pi epsilon 0 small r, where r is your radial distance from the center. So there, whatever is concerning us is just the total charge that is enclosed by the Gaussian sphere that we are considering. So it's important to remember that this holds only for potential inside a uniformly charged sphere. And because of the continuity of potential, it obviously holds on the surface as well, right? So now we'll use this relation to solve a question, okay? So here it said that we have two uniformly charged insulating solid sphere, A and B, both of radius A, okay? One carries a positive charge plus Q, another carries a negative charge, and they are touching each other, okay? So now we want to find, we say that the potential at the center of this sphere A is VA, and that at the center of this other sphere is VB. We want to find the difference between the two, right? So can you tell me how to do that? You have to remember that potential satisfies the superposition principle. So at each point, you have to first find what is VA, you have to find what is VB. Okay, And when you find VA, you would be having contributions from this sphere as well as from this sphere. Again, when you are finding VB, you have contribution from this sphere as well as from this sphere. So can you tell me what would be the expression for VA? So there you have to use this relation that we just obtained. Just as a hint, I can tell you that you have to use the relation for the potential at the center of a solid sphere of radius r with some total charge q. That is, you have to put z equal to 0, and then you get the potential as 3q by 4 pi epsilon naught r. So that is the relation that you have to use here, because you are finding the potential at the center of this spheres. So what is VA? Anyone? First, tell me what would be, like, qualitatively, what would be VA? And then we can try to derive the expression for VA.
The VA should increase, means if we are bringing opposite charge in contact with the positive charge, so the reference is going in opposite direction and with the same amount. So it should
So
increase.
why do you say the same amount? See,
It's plus Q and
yeah,
minus Q.
plus Q and minus Q. But one thing you have to remember, so when you're finding potential VA, you have two contributions, one for this sphere, one for this sphere, right? So for this sphere, you are finding the potential at the center of a positively charged sphere of total charge Q. And then what is the contribution of this charge, this sphere? There it's at a distance of 2a from the center, right? The distances of, so this is your field point, the center of the sphere, right? But the contributions from both the spheres are not the same, because in one case, for one sphere, you are at the center of the sphere. For other sphere, you are at a distance of 2a from the center. Do you understand? So first tell me, what would be the potential at the center of this sphere for this positive sphere? Just forget about the negative charge, negatively charged sphere. What would be the potential at the center of this sphere for just this sphere?
It's 3q by 4 pi epsilon r.
R or A? For this case, radius is A. Okay. Okay. And similarly here, what would be the potential for this sphere? Forget about the positive charge now, positive sphere now. It would again be
3q, same but negative.
yes, minus 3q by 8 pi epsilon naught A, right? Now, what you have to consider is, now consider just this case that you have this sphere, okay, some sphere, negatively charged sphere of total charge Q, and you want to find a, like it's something like this. Wait 1 second. So now what I'm telling you to consider is, sorry, it's in no way a sphere, but consider this is a sphere, okay? And this has a negatively charged, okay, all over it. And now you want to find the potential somewhere here, okay? And you know the distance from the center is how much? It's 2a, right? So the distance from the center of the sphere is 2a. You want to find the potential at this point for this negatively charged sphere. So what would that be?
integrating over this line.
See, what would be the field for, like, first think of field, right? What would be the field for this sphere at a distance of 2a? Use the Gauss's law. Consider that you have another sphere here of some, oh, sorry, just 1 second. 1 second, I did a mistake. So what I mean here is that you have some sphere, okay, and this has some radius of a, and then at a distance of 2a, you want to find the field, okay, and it has a negative charge. So what you can consider is you can, okay, this is very bad. Okay, so you can consider another sphere of total radius 2a, right? And then use the Gauss's law. So then that would directly give you the field at this point. Am I making sense? Like, consider a Gaussian sphere. This is a Gaussian sphere, and this is the sphere whose field you want to find. It has a negative charge. So over this surface, if you do an integral, what would that be? E into 4 pi
2a square,
2a square would be equal to the total charge that is enclosed, that is minus capital Q by epsilon naught, right? So that will give you the field at this point, right?
Right.
Right. And you know how potential and field is related? Field is related as E equal to minus grad V, right? So in a way, if you integrate E, if you do a line integral of electric field, that gives you the potential, right?
Yes.
So that means, how will your potential vary? It would vary as 1 by 4 pi epsilon 0 Q by R, just R. Your electric field varies as 1 by R square. Your potential goes as 1 by R, right? So that means if you have some sphere, so some sphere of some total charge Q, anywhere outside the sphere, the potential would be equal to 1 by 4 pi epsilon 0 Q, that is your, like, the charge on the total charge on the sphere, by the distance from the center of that sphere. Is it clear?
Yes.
So what would be the value of potential in this case? So value of potential at this point for this sphere.
Q by 4 pi epsilon by 4a.
Q by 4 pi epsilon 0 by 4a, minus of that, right? Minus Q. Right? And then similarly, you know what would be the expression? 1 second, where is the cursor? Again, similarly, you know what would be the potential at this point for this sphere, right? It would be plus Q by 4 pi epsilon naught into 2a, right? So now, if you consider all these contributions together, what do you get? You see that VA has two contributions, one due to sphere A, okay, this is for sphere A, another due to sphere B, right? And here again, VB has two contributions, one due to sphere B and then due to sphere A. So this is the final potential at the center of the sphere, and this is the final potential at the center of this sphere. And what you have to find is VA minus VB. So if you do that, what you get is this. Is it clear?
Right.
Okay. So clear to everyone? Others can follow, right? I hope yes. So I think this was it. Now So that's it for today. If you have some particular doubt regarding anything that we discussed or anything else, you can ask me now.
For the question that we solved for the potential using the Poisson's equation, I think it's the second or the first question, where we have the fx function.
Oh, okay. FX. Acha, this one.
Not this one. We potentialize the function of phi into e to the power minus r by r naught, right?
Yeah, this one. Yes.
So by looking in at this expression, if I directly put the value of r equals the value of r as r equals to r naught in this expression, and then find the delta del by del r. So
Then it would be
I think
0. Is that the question?
right.
Yes, but that's not how it's done, right? See, when what you are then doing is you're already putting. So what do you have to do? You have to find what is derivative. Derivative is rate of change of some quantity, right? So a quantity has some, so it has some functional form. Now you want to find what is the value of that rate of change of that quantity at some point. Now, if you already put the value of that point initially, what you are doing is you are losing on the information of the functional dependence of the term, right? Whenever you're doing derivative at derivative or integration or whatever, what do you do? When you do integration, what do? You first try to look at how the function depends on, suppose if it is a function of some x or y, you see how the function depends on x or y. You do a integration, okay, which takes into account this functional dependence, and then you put the value at the points where you want to find it, right? When you do, suppose, definite integral, what you are doing is you are first trying to solve the expression, solve the like considering the functional dependence, you get an expression, and then you go to those individual points at the limits and you put those values and solve, right? But if you do that initially, what you are doing is actually you are losing, or wrongfully you are losing the information of the functional dependence. Here it's a function of r. So this function tells you how phi changes as a function of r. And what the question is asking is, if this is how phi changes as a function of r, how does del phi del x vary, or what is the value of del phi del r at some point r equal to r naught, suppose. So that tells how phi, that is the question there it's asking is how del phi del r is, or what the value of del phi del r is, that is how phi is changing as a function of r at that point. But now if you directly put any value of r here, okay, like any positional value, that means you are losing on the information of the positional dependence. Then it's no longer a function of r, right? That then it's a constant. You understand my point?
Okay.
So
Got
like
got.
this function has the information of how phi changes as a function of r. You have to retain that information and use that information to see how del phi del r varies at some particular point. But if you directly go put that value there, then you no longer have the positional dependence. Then it's just a constant. That is just the value of phi at that point. You want to see how phi changes as a function of r. You don't want to see how the particular value of phi at that point is changing. That the particular value of phi at that point is just a constant. Understood, right?
Yes, thank you.
Yes. Okay. Any other doubt? Okay, if not, then I would just tell everyone to remember these things. Okay, so this is the take home message of today's class. Like, yeah, you should be able to understand how you get to these expressions and what this tells you. Okay, and when to use it. So depending on the question, you have to choose which relations are useful for you. So suppose you know what is your potential, you want to find the charge density, then you have to use this relation. But if you are given electric field and you want to find the charge density, then you have to use this relation. Okay, and then if you have to suppose you know the potential, you want to find electric field, then you have to use this relation. Again, if you know the electric field but you want to find the potential, then you have to use this relation. So depending on what your question is asking, you need to remember and understand which relations to use. Okay, so this is the whole crux of today's class. And obviously, for solving this kind of questions, you should be well versed about how to change from one coordinate system to another. So you should be knowing how to write the gradient, divergence, and curl in different coordinate systems, especially the spherical and the cylindrical coordinate systems. And for that, you can refer to the last class also, where we talk about how to move from from the rectangular coordinates to any curvilinear coordinate system. Okay. And if no one has any further doubts, then let's call it a day. Okay. So bye guys. Thank you.
Thank you.
Thank you.